Alright, so now we're on problem 11b, and we want to do the same as we did for problem 11a and find the Maclaurin series for this function, also find the first three terms and the radius of convergence. So the way that we're going to do this one is a little bit different than the last one, but either way, we're going to write our Maclaurin series for e to the power x. So we know the Maclaurin series for e to the power x is just starting at n equals 0, going to infinity, x to the power n over n factorial. Okay, and so we can write these terms out. We'll write a few terms out just to kind of see what happens when we subtract 1 and then divide by x. So this is going to be equal to, for n equals 0, x to the power 0 divided by 0 factorial is just 1. And then the next term is x divided by 1 factorial, so this is just x. And then it's x squared divided by 2. And then so on and so forth. We don't need to write really any more terms out right now. So then when we do e to the power x minus 1, we see that we just lose this 1 in front of this power series. So we're going to get the remaining term, so we'll have x plus x squared over 2 plus x cubed over 6, and so on and so forth. And if you want to write that out as a power series, now we're just starting our terms at n equals 1 instead of n equals 0 here, because our n equals 0 term corresponded to 1, and we didn't lose any of the other terms. So we're just writing x to the n over n factorial. And notice the difference between what I just wrote and what I wrote previously was that n started at 0 for the original power series for e to the power x, and for e to the x minus 1, it starts at n equals 1. Okay, so now we want to take this power series and divide by x, and so that'll be a way to represent this function as a power series. And we know that if we represent a function as a power series with center at 0, it has to be the Maclaurin series for the function. So this is how we're finding the Maclaurin series for this function. So either way, we look at e to the power x minus 1 divided by x. So in the numerator, we know that this is the power series x to the n factorial, and starts at 1, goes to infinity, and we're dividing by x. So dividing by x is just subtracting 1 from the power of each term for x. So this is just going to result in the power series n starting at 1, going to infinity, x to the power n minus 1, divided by n factorial. So this is our power series for e to the power x minus 1. So this is our Maclaurin series because it's centered at 0. So now we want to write the first three terms for this Maclaurin series. So the first three terms are going to come from n equals 1, n equals 2, and n equals 3. So when we plug in n equals 1, we get x to the power 1 minus 1, so this is x to the 0, divided by 1 factorial, but either way, x to the power 0 is equal to 1, so this is 1 over 1 factorial, so that just equals 1, but we'll write it in a second. And then we add, when n is equal to 2, this is x to the power 2 minus 1, so x to the 1 divided by 2 factorial, so this is x divided by 2 factorial, plus the next term is x squared divided by 3 factorial. And then, of course, we have infinitely many terms that we're not writing, and so we just write a couple dots, and that indicates this fact. But of course, we can rewrite these terms as 1 plus x divided by 2 plus x squared divided by 6, and then plus dot dot dot. Okay, so this is our Maclaurin series. Here are the first three terms of the Maclaurin series for this function, and now we want to find the radius of convergence. Okay, so to do the radius of convergence, we want to do the ratio test. That's the way we're going to prove it. But essentially, if you think about it, this is so closely related to the function e to the power x, you're going to expect the radius of convergence to be plus infinity, but that's exactly what we're going to show by doing the ratio test. Okay, cool. So I need to look at the ratio of the nth term to the n plus first term. So a n plus 1 divided by a n. See what this limit is as n goes to infinity. So our n plus first term is equal to, so here is our nth term in general. So this is going to be x to the power n divided by n plus 1 factorial. And then our nth term is x to the power n minus 1 divided by n factorial. And so I probably shouldn't have written this limit, so actually let's just go ahead and forget about this limit for 1 second. Let's just simplify the ratio that we have, and then we'll take the limit once we have it simplified. So either way, we're left with 1 power of x in the numerator, and we don't know if x is positive or negative, so we can go ahead and just keep the absolute value of x. But of course, it's coming from the fact that we have 1 larger power of x in the numerator, right? So those go away, that turns into 1. And then we have an n factorial in the numerator, right, because it's in the denominator of the denominator, and then an n plus 1 factorial in the denominator because it's in the denominator of the numerator. So either way, this leaves us, so n factorial is just 1 times 2 times 3 all the way up to n. N plus 1 factorial is just 1 times 2 times 3 all the way up to n, and then also multiply by n plus 1. So we can cancel the first n factors here, so we can get rid of this, and that basically just gets rid of the factorial down there, and we have absolute value of x divided by n plus 1. But if you think about it, for any value of x, we fix that value of x, and we're letting n tend to infinity, and this term has to go to 0 in that case because the denominator blows up and the numerator stays constant. So either way, we see that our limit of successive terms, so the ratio of the successive terms, is equal to 0, and that implies for us that the radius of convergence is plus infinity. All right, so we got our Maclaurin series, our first 3 terms, and our radius of convergence, and that finishes part B for us.